Good afternoon. I'm Johan Nell, and this afternoon I'd like to talk to you about how digital twins are being given a new lease of life through the energy transition and drives a new purpose for digital twins, especially in older brownfield assets. I'd like to offer that it's possibly even more important than ever to pursue digital twins for older assets when we know the business case hasn't been all that compelling. Digital twins have a significant role to play in optimizing our current oil and gas assets. Of course, by enhancing the understanding of value drivers, production bottlenecks, and obstacles, but also in optimizing the UK and indeed other basins' energy landscapes of tomorrow. Digital twins are becoming increasingly instrumental to the integration of the various components of our evolving energy system. This need is particularly important in the light of the North Sea transition deal, which of course is aiming to drive down and eventually eliminate emissions. And there are big incentives on offer for the oil and gas industry. Today, I'd like to share with you how digital twins can support these objectives for the oil and gas industry, and of course, some of the broader challenges we collectively need to resolve. We know that digital twins are gaining traction in oil and gas, and there are some progressive adoption plans. However, there are differing perspectives and indeed confusion about the value and definitions and indeed approach to digital twins. Let me offer a little bit of context, especially around the UK oil and gas sector. We know that for the foreseeable future, it will remain central to the energy supply of the United Kingdom. Oil and gas still meets in excess of 70% of the UK's primary energy needs. It is part of an interconnected system. The UK imports approximately 35% of its primary energy and gas from especially Norway as the primary source. It is fair to say that energy imports are slowly declining with some of the new sources under construction in the UK. But there's also been an increase in LNG imports, which has a carbon intensity double that of locally produced gas. And that, of course, isn't helpful from an emissions perspective. The OGA, Bayes and others estimates the North Sea has the potential to contribute to as much as 60% of the UK's emission abatement requirements by 2050. And it's estimated that half of this is achievable by integrating the energy landscape across hydrocarbon production, hydrogen, renewables, and carbon sequestration. The North Sea Transition Deal sets out an ambitious plan to meet stretching greenhouse gas emission reduction targets, with a 60 million tonne reduction in greenhouse gas emissions and investment of up to £16 billion by 2030. That investment in new energy technologies to enable CCUS and hydrogen at scale. There are a number of planned or current developments to take advantage of this investment, and that includes Zero Carbon Humber, Net Zero Teesside, Acorn, Shetland Energy Hub, Aberdeen Energy Transition Zone, some local platform electrification, and other plans. A large proportion of these developments includes existing brownfield infrastructure, which has without exception operated outside of its original design envelope and comes with the inherent integrity and operational issues of connecting old to new. The digital twin has an important role to play to optimize the energy landscape in the UK by mapping the real world into the virtual and connected with advanced systems and mirrored assets both virtually and in real time. So let's for a moment just consider the application of digital twins. The digital twin, as you will hear this or would have heard this morning and hear for the rest of the day and tomorrow, is a virtual representation of a physical asset or system, or indeed group of assets, and enable operators to monitor, visualize, or simulate static and dynamic asset characteristics. The digital twin differs from an integrated asset model in its connection and mirroring of the actual asset. While there are industry frameworks and recommended practices for building and assuring digital twins, there are limitless definitions for best practices, especially when evaluating the viable design, implementation, and integration options for digital twins, or just integrating various twins across an integrated system or interconnected system. Mid-tier or smaller oil and gas companies with limited resource are struggling to make progress, especially when given the competing and at times opposing pressures on resources and budgets. The value versus effort and cost equation remains a well-debated challenge. Assembling contextualized plant data, integrating tools and systems, developing monitoring and analysis tools require time and effort, which competes with day-to-day operational activities. And this is especially true if uptime, plant efficiency, and production optimization are the key drivers. Investment payback versus the planned cessation date needs to make sense to justify these investments or redirect scarce effort. The result is an array of limited asset digital representations and flow assurance models. We know that digital twins rely heavily on the existence of good quality, well-governed data, which often proves to be an early stumbling block. However, if we are clear on the problem we are solving, do we need that ideal data set? Let's consider the question we are really trying to answer. So, is investment still warranted to create these digital twins for aging plant in the North Sea? Well, significant effort and investment is required for these brownfield assets, and there is a question that must be asked about the business case, and it must be asked on an asset-by-asset, case-by-case basis. What questions are we seeking to answer, or which questions do digital twins enable us to better ask of our assets and its performance? To be successful, digital twin implementers need to reconcile stakeholder differences and uncertainties about the right design, implementation, even the maintenance of twins, or the governance strategy of those twins. They'll be challenged by the cultural barriers, i.e., doing things differently, that operation teams hold dearly, to both maintain and operate those twins. I would contest that brownfield digital twins require a different mindset if you are going to make the right progress. We know that for brownfield assets, operations can use digital twins to enhance the understanding of the value drivers, production bottlenecks, and obstacles. But even at asset level, the end-to-end production system is seldom adequately twinned. For some of the plant in the North Sea, new challenges are emerging, which may warrant some of this investment. Emerging oil and gas companies now own or plan energy assets across the energy spectrum. A client of mine, for example, has to consider across 4 basins a big plug and abandon challenge, on offshore gas operations, a new hydrogen investment, older assets, more traditional assets in the UK continental shelf, and modern fields in the Norwegian sector. A complicated issue. In particular, operators have the opportunity now to analyze if and how existing infrastructure could play a role in the overall emissions reduction and energy transition commitments they've made, especially if we move to a situation where we start to manage carbon as if it is production, and to deal with the sentiment and the impatience of shareholders and lenders. It is our view that the digital twin has an important role in the energy landscape of the UK, especially in the light of the North Sea transition deal and the overall investor sentiment. A fit-for-purpose digital twin will greatly contribute to informed optimization decisions. It will give operators the ability to carry out simulations and what-if analysis and choose the optimum extension, cessation, or indeed decommissioning option. Digital twins will increasingly be instrumental to the integration of various components of this energy system and will drive the dynamic model of that system against production optimization, emissions reduction, and energy security challenges. This use of the integrated digital twin to optimize at an overall systems level rather than an asset or component level will, to my mind, be a step change in the use of digital twin and one that will drive great overall benefit. Let me give you an example. If we were able to model how hard the turbine and compressor was working under current conditions, including high sea line injection, low atmospheric pressure conditions, we could establish how much more carbon we were emitting than if the equipment was performing at ideal efficiency. And that's before we even consider the impact of different set points for different shifts or demand peaks. Greenhouse gas emissions, a complex interconnected energy system, balancing demand, balancing supply, security, and client impact needs all need to be considered jointly. The ability to model and analyze this system to balance all of these challenges is a complex task and is impeded currently by systems integration, diversity of the components involved, and the fact that various parties own these components. So what are examples of the new demand on digital twins? There are several examples emerging where a combination of existing or reconfigured plant and new plant will form this interconnected energy system. As an example, the Zero Carbon Humber initiative includes modification at 2 power stations including DRACs, carbon capture and storage infrastructure, a hydrogen plant, and renewables production. And all of this is interconnected to the local industrial and domestic sources of demand. Each component in this system delivers energy at different levels of efficiency and reliability, and the investment required to digitally model and analyze each component varies. This requires well-considered digital strategies, including how these components will be integrated and how to achieve cooperation between the various owners of the system in order to achieve interoperability. Being able to model and track the actual system's behavior of energy supply, the demand of energy, pricing, the competitive sources, all in the context of rules and regulation at hourly intervals in a distributed system is a complex endeavor. And there are only a few companies who get close to being able to do so. Add hydrogen options, carbon cost, as well as hydrocarbon pricing to the mix, and this model becomes tremendously complex. It goes way beyond a physical asset point, cloud, laser scan, and 3D models. And as an aside, modeling demands now even include the analysis of the physical and financial risk under various climate scenarios, with real-world data on actual emissions as the input to these models, and of course the optimization parameters for the overall energy system. So where does this leave us on the spectrum of digital twin applications? Digital twins have 3 progressive roles: monitor, analyze, and model. The level of granularity at which digital twins are created and connected to form a platform of twins should be driven by the requirement of the system. We are all very familiar with the application of digital twins in operations, where simulation twins facilitate asset performance optimization by predicting future operating parameters across a range of conditions or scenarios. Simulations or predictions of future asset states or behaviors, however, use algorithms which can either be physics-based or analytics-based. As an example of a physics-based model, and related to the energy transition, computational fluid dynamic modeling of emissions or the behavior of gas dispersion clouds is an application. As an analytics-based model, Here, algorithm types are sometimes combined with physics-based engines and works in conjunction with analytics, machine learning, or other AI techniques to enhance the range of accuracy of predictions. Some oil and gas EPCs are already leveraging simulation twin capabilities by combining previously standalone mechanical and process models to provide engineering simulations and to automate systems testing. The need to monitor, analyze, and model a system of which current, sometimes older production assets is a single component means that a different and more nuanced approach can be taken to developing the digital twin. This requires a deliberate strategy for the system involved. It is much easier to develop complete digital twins for new plant during construction, and hence for older plant, the minimum level of detail to model and analyze the whole system needs to be determined. So what next for plant owners and suppliers? Well, we face the challenge of developing digital twins in an environment where it's both difficult and seemingly not cost effective. This has changed little from a pure production efficiency perspective. However, production efficiency now competes with emissions constraints, all within this complex system that I described. With governments levying increasing carbon prices, the paradox of more production versus lower emissions becomes more complex, and the ability to accurately model this is crucial. For example, break-even point shifts for energy-efficient modifications and for offshore electrifications. Companies need to be able to model this accurately in response to the carbon tax challenges. And just as an example what carbon tax implies, Norway plans to more than triple the carbon tax it levies on its oil and gas businesses, from approximately $75 to $240 by 2030. And of course, the country's powerful oil lobby didn't appreciate that. But these are the challenges that we need to overcome. To develop integrated digital models across this landscape will require strategies and standards to come together. Interaction between a broader group of technology and expertise providers is needed. They represent systems dynamics, modeling, analytics, machine learning, and data architecture capabilities. Companies should continue to develop flexible solution and data infrastructure and use proven tools, but look at the process as a journey rather than a one-off event. Moreover, it will require a good understanding of the role of the digital twin in each component, but with a clear understanding of the baseline to create a functional model. Technology vendors should continue to develop efficient approaches to establish minimum viable twins, but have its intended purpose in mind and accept that a one-size-fits-all model is not required. So, I'd like to conclude with a few remarks. Connecting digital twins across the emerging components of the local or extended energy system, which includes oil and gas, renewables, hydrogen and CCUS, will be increasingly important. It will provide insights, enable analytics, and the application of artificial intelligence to determine solutions to solve energy and emissions balance challenges. And therefore, I contend that we should twin the whole energy system, not just each component or asset, and hence optimize at system level across components. We need to consider all aspects, especially emissions, in the design of the twinning solution for every asset by taking consideration of the nodes and the networks around that asset. We should then implement and indeed over time optimize that fit-for-purpose, nuanced approach for the capabilities required and the components as part of the system that we need to add to the overall basin. New questions are now emerging that requires us to rethink and reimagine the motivation for digital twins for both old and new energy assets. We should develop digital twins for these requirements. Thank you.